Okay, so now we're going to have a series of videos that go through some quantitative concepts dealing with equilibrium. And the first one is going to be a very important concept dealing with what's known as an ICE table. You'll see why it's known as an ICE table in a minute. But this important step is usually done for pretty well every equilibrium calculation you're going to be faced with. So get used to the idea of building up this table. It's pretty straightforward. It shouldn't take too long for each problem. And as we progress, you'll see how we can actually simplify things, make the construction of the ICE table even easier. But as I said, it's a pretty important step. You want to be in the habit of doing it for every problem. So let's have a look at one. All right, so it's basically constructed so that you can determine equilibrium concentrations. If you remember, an equilibrium expression, Kc, can be filled in with values at equilibrium. So we have to find equilibrium concentrations in many instances. So let's deal with this hypothetical reaction. So we have A plus 2B yielding 2C. And initially, we have 2.0 moles per liter of A. And it's added to a reaction vessel that contains 2.5 moles per liter of B. So we have concentrations of A and B prior to mixing, and then we can assume they mix. And as it says here, when the system reaches equilibrium, the concentration of C is 0.50 moles per liter. So we do have one equilibrium concentration, but we need all equilibrium concentrations. So we construct an ICE table. An ICE table basically stands for initial concentrations, the change in concentration, and the equilibrium concentration. And so we can start filling in this table because we have some information. 2.0 moles of A initially, so 2.0 moles per liter. 2.5 moles per liter of B initially. Now, we don't have anything about the initial concentration of C, but here's the thing. Unless you're told otherwise, we assume the reaction hasn't started yet when we have A and B. Therefore, the initial concentration of C is 0. And you're going to see in many instances that's the case. The initial concentration of products is going to be 0. We do have one more piece of information. At equilibrium, concentration of C is 0.50 moles per liter. 0.50, so we know that. Basically, we have to fill in the rest of the table because what we want are all equilibrium concentrations. So it's not that hard because we have enough information to do this. We started with 0 moles per liter of C. We now have 0.50 moles per liter at equilibrium. So that change there must have been 0.50 moles per liter. That is, the concentration of C increased, that's what the positive sign implies, increased by 0.50 moles per liter. Now, because of stoichiometry, we can find the rest of it. And go for the easy one first. Stoichiometry is basically these ratios, and there's an easy ratio, a 2 to 2 ratio, the same as a 1 to 1 ratio. So we know the change in B. It's the same, only it's negative. The concentration of B decreased. Now we can look at stoichiometry of between C and A, or you can look at it between B and A. It doesn't really matter which one you look at. And again, for every 2 moles of C that was produced, 1 mole of A reacted. So what's the relationship there? Well, if you wanted to quickly figure that out, if you're not really sure, what we're looking at is concentration of A equals concentration of C times an equation factor. So this is from, you remember grade 11 stoichiometry. And so the change was 0.5 times 1 over 2. 1A to C. And so 0.250 was the change. So negative 0 or minus 0.250 moles per liter A in terms of change. Now we just do the math, and this is why it's useful to put in the sign. So 2 minus 0.25, 1.75 moles per liter. 2.5 minus 0.5, 2.0 moles per liter, and 0.5 moles per liter. So now we have all of our equilibrium concentrations, which leads us to our next question. If that's the case, once we've determined equilibrium concentrations, what can we do? Well, then we can determine the value of Kc. So let's look at this problem. So here's another problem. The formation of ammonia. And before we get started, we got to make sure the equation is balanced. So N2 plus H2 yields ammonia, NH3. But it's not balanced, so to balance this, we're going to make this a 2 to balance the nitrogen. We're going to make that a 3 to balance the hydrogen. Now we have a balanced equation. Now we can start constructing our ICE table. So here's our ICE, initial change equilibrium, and we have some concentrations. Initial concentration of nitrogen is 0.32 moles per liter. Initial concentration of hydrogen, 0.60 moles per liter. And we know what the initial concentration of ammonia is. It's nothing, because nothing's happened yet. Now we can start working on filling in the rest of the ICE table. And here's the other useful piece of information. At equilibrium, concentration of hydrogen is 0.30. So at equilibrium, 0.30 for hydrogen. So we can calculate the change, minus 0.30. It must have decreased by 0.30 moles per liter to leave us with an equilibrium concentration of 0.30. So now it's all about stoichiometry, and again, this is a 3:2 ratio, so the change is not going to be the same, but the change is going to be positive because we're talking about a product, and it's going to be 0.20 moles per liter. This is a 3:1 ratio or a 2:1 ratio, whichever one I'll look at it. That said, it's also a decrease because it's a reactant, and it's going to decrease by 0.10 moles per liter. So we can fill in the change because we just calculated the change of hydrogen. Allows us through stoichiometry to get the rest of it. And so now the math is pretty simple. This is going to be 0.22 moles per liter. We already have 0.30, and this is going to be 0.20 moles per liter. So again, now we have equilibrium concentrations. And so we can carry on with this to find the answer. The answer is, what is the value of K? So the next thing we need is our equilibrium expression. So Kc equals, and if we just quickly go back, make sure we look at our NH3, ammonia, squared. N2 of 1, H2 cubed. Now we can just substitute in. And our values, again, from our equilibrium were 0.20 squared, 0.22 times 0.30 cubed. And so when you plug all that into your calculator, you come up with an answer of 6.7. So the equilibrium constant Kc equals 6.7. And if you think about that value, that should make sense. It's sort of between 0.1 and 10, and if you remember about the extent of the reaction, we look at something between 0.1 and 10, an equilibrium constant in that range, implies that the concentrations are not that different between products and reactants. And they aren't that different if you think about it. Here they are at equilibrium, 0.22, almost identical, 0.2, 0.30, pretty close to 0.20. So again, it kind of makes sense that that equilibrium constant value of 6 is 6.7. It's in the range we would probably predict. And so that's how you use an ICE table and determine values of Kc from equilibrium concentrations. So that concludes this video.